All right, this is the last audio check. Someone just put in the chat if they can hear me, and if so, we'll get going here. Awesome. All right. And then everyone should have been able to get the data sheet that's associated with this copper that we're going to be discussing today off of the initial registration email. But if you don't have it, my email is in the chat. Just send me an email and I'll get it over to you this morning. All right. So let's get started. So the first pure 3D printed copper. All right. First, I'm going to go over just our agenda, and we're going to be talking about why Markforged copper. We're going to take an overview, look of the properties of this specific alloy. We're going to go over a real-world case study from an automotive manufacturer. And then lastly, we're just going to take a walk through Eiger, which is the slicing software that the MetalX and all of the Markforged ecosystem uses. And then all throughout the presentation, feel free to put some questions in. And at the end, I'll go around and answer them all. All right, so why Markforged copper? And why are we calling it the first pure commercially available 3D printed copper? Well, the main reason is with DMLS, or direct metal laser sintering, it's very difficult, if not impossible, to print with pure copper. And this is due to the reflectivity. So the laser isn't able to properly sinter that material. So for that reason, all the past 3D printed coppers have been alloyed. And I mean, it makes it possible so you can print it on a laser system. But for that, you're trading some thermal and electrical conductivity. So with pure copper, you get very similar, if not identical, to machined or brazed copper in terms of the electrical and thermal conductivity, but you're given access to a lot more complex geometries, things that you wouldn't even be able to do with other machining processes. Also, it's a competitive price point. If you were to shop out 3D printed copper or just a complex copper part, chances are it's not going to be cheap. But a 200cc spool of Markforged copper is only about $300. Reduced lead times. If anyone's worked extensively with copper, you know that it's not fun to machine or braze repeatedly. And oftentimes it takes a long time to get parts back, either from the shop or outsourcing. But when you print on the Markforged system, it's as easy as printing any other FDM style 3D printed part. So you get your part within a couple of days as opposed to a few weeks. And lastly, one of the best parts of this platform is you don't need any sort of specialized safety equipment. The system is office friendly. It only requires a few facility changes, but it's mainly just airflow. So with Markforged 3D printed copper, you're able to optimize thermal design. So here we have a ton of different heat sinks that are complex, and if you're looking at these and thinking about machining them, you're probably thinking that would be a huge pain, especially this curvy one down here on the bottom left. But with 3D printing, you get significant design freedom. You're able to try multiple iterations very quickly and land on the best option for you, as opposed to maybe trying one, but now you're out of time and you have to stick with your first design or second design. And with this 3D printed copper, you're also getting ease of electrical transfer that you're not getting with other metals. You're able to make functional prototypes as opposed to maybe doing a fit check with a metal piece. And you can actually make end-use parts with a lot of these on the lower quantities. So let's take a deep dive into a very specific application in the automotive industry, which is spot welding shanks. On the left, we have the machined version of of the copper spot welding shank, and on the right is the 3D printed version. Obviously, visually, they're pretty much the same. The one on the left is a bit older, so it's a little oxidized. But other than that, look-wise, they're almost identical. But with copper, the most important thing is the conductivity. So here's a chart comparing the traditional manufactured shank, which is on the left side of this chart, to the 3D printed version. As you can see, the original shanks were clocking in at about 57 to 63 microohms, while the 3D printed versions, it's a little bit tighter, it's 62 to 64 microohms. So very, very similar performance-wise, and compared to the manufactured machined shanks, but they get to the shop floor significantly faster. You can get one of these out on the shop in about 3 to 4 days. And then, in case you didn't see on the top, sort of where it sectioned off between traditional and the 3D printed versions, over here on the left, you've got the traditional, and over on the right, you have the 3D printed. And like I was saying, it's very consistent from weld to weld. You don't have spikes and valleys in the testing here. Everything is consistently maintained between 62 and 64 microohms. So here's a quote from the global automotive manufacturer. Basically, they wanted to express that they're very impressed with the Markforged Metal X system as a whole. They had the machine before they had copper, but now that they have copper, they're able to print applications like this, which would take weeks and weeks to get back. And if they want to go through multiple iterations, in the automotive industry, especially these large manufacturers, any minute that you save is thousands and thousands of dollars. So any way that they can get their parts quicker is a huge win for them. And they're actually able to reduce inventory costs by around the cost of the whole system with this application. So lead times are reduced by 12 times. The part cost was reduced by about 6 times. And like I said, just with one system, they were able to reduce their inventory costs by the cost of that system. So they made their money back on this application. So now I wanted to take a walk through Eiger, which is the slicing software that we use for the Metal X. So I'm going to try to change the screen over to Eiger real quick. Once it changes over, if someone could just let me know that they can see, it should now look like a Chrome browser screen. Awesome. All right. So this is what Eiger looks like when you log in. I'm using the cloud version, but there's also on-premise desktop versions of this software. When you first enter, you're able to create a folder, which is what we're in now. And once you're in there, you're able to import your STLs. So once you click this, click your file and open it up, it's going to look a lot like this screen here. It's going to take a minute to load because I'm both streaming this and accessing this through the cloud. So just give it a minute here. All right. So you've got your part here. When it initially uploads, you're able to choose the units. So if it's obviously the wrong units, you're able to change it here. You choose your post-sintered layer height. And the reason you do that as opposed to the printed layer height is because in this process, it's very similar to metal injection molding. The part is printed with a binder, and then that goes into a wash and then a furnace. So it's roughly 20% larger than the end part that you get. So you want to choose what the layer height is going to be after you get your end use part. All the scaling, even specific geometries, is all done in Eiger, which is constantly learning from other people's geometries and Markforged as a whole. So you benefit from the machine learning aspect of it without having to actually input any of that yourself. So you're not having to adjust the scaling up in CAD. Eiger will do all of that automatically, and every day it gets better. So you choose your material here. I'm choosing copper because that's what we're talking about today. However, we do have other materials available from 17-4 stainless steel, Inconel 625, H13 tool steel, A2 and D2 tool steels, and then we have a titanium on the way this year, as well as a different stainless steel. Then you choose your sinter furnace. So the sinter 1 is the smaller furnace that Markforged offers, and the sinter 2 is the larger one. Just for today, we're going to choose the sinter 1 because that's what we have at our shop at Neometrics. Scale, I've scaled this part down to 0.75. That was the directions for this specific piece here for trade shows, essentially. Then you've got sinter stability. What this means is it will change certain aspects of the geometry to make your part sinter better. So if it's a long post that's just sticking straight up, when you put that in the furnace, obviously it's going to bend over and not going to be able to maintain that shape. So for certain complex geometries, you're able to click this on. It's not going to do too much to the shape of the part. It might thicken walls here or there, but it makes your part print better overall after it comes out of the furnace. And then there's a few things that are in alpha. Markforged is always testing new ways to make their printing system better. So this leak resistance. So what that means is when you print your part, you can have fluid run through it, and none of it's going to come out. So on an FDM printed part, obviously that's not always the easiest thing to do, but Markforged is working to make that happen. So right now it's an alpha, but probably later on this year we'll see this go fully live. But you can still use it now and test it out. And you can do things like disable the raft. So it prints a raft underneath your part, which we'll see once we go into the internal view. If your part is a little bit too big for the furnace with the raft, you can disable it if it's a geometry that you feel will shrink uniformly. But that's all the raft does, is it helps your part shrink in a uniform way. And then support structures, let's say, so for this part specifically, we don't have any supports since there's no real overhangs that would require it. But let's say you have a part like a cylinder, and then it's got a support ring that goes all the way around it. That would be not easy to get off on its own. You're able to play around with cubic or radial separations, and what that means is it breaks the support structure up for you. So after it sinters, you're able to break it apart and get those supports off easily. You can also change up the infill, just like any other 3D printing platform. With copper, we're going to go with solid fill because for the thermal and electrical conductivity, we want it to match as close to as possible to a machined version of copper. But for these other materials, you can play around with triangular fill with different percentages, different wall thicknesses in roofs and floors, and this will give you different strength. But it also saves you a lot of time if you do an infill pattern. Let's say you wanted to print and then wash it. If a part's solid, it'll take a lot longer to print and a lot longer to wash, just because it's more material and it takes longer for that wash liquid to penetrate. So great. Now we've got our part imported. We have all the settings that we want specifically for this metal part. Now we'll go into the internal view, which also may take a second to load. But here you can now see this is exactly what the part is going to look like when it's 3D printed, and this is our X-ray view. So it looks a little bit blurry, and it's because you can see every single layer as it's laid out, including this raft that goes around. So if we go to the 2D view here, we can go layer by layer and look exactly where our part is here. So we're building up from the bottom. And we'll go back to 3D. One thing in relation to those complex support structures that I was describing before is if you have a layer that you wanted a specific release layer at, you click this and it will cut that support. We don't have any support here, so I can't show you on this specific part, but it'll put a layer of ceramic at that layer height. And what that means is when it comes out of the furnace, you're able to break that part off, so it just chunks your supports up a bit easier. But yeah, this is our final part. We would click print here. It puts it on a build tray once it loads the part in. And you can put a few of these here. You can put different parts. If you go to add parts here, you can add, let's say this one as well. And you can put a few at a time. It gives you your estimated print time, the volume of the copper, so it's about 200 cc's for a spool, and then it gives you your material cost, and then how much ceramic release that you're going to be using. On these two parts, I think the only ceramic release is going to be in between the raft and the part here. I'm going to check now the chat to make sure there are no questions about Eiger specifically while I have it open. Great. All right. So I would hit print. It would put it on the Metal X if it was set up. Right now, our Metal X has stainless steel in it, so I'm not really allowed to send this part over, but I can add it to the queue. So if I do that, next time I go over to my machine, I can load up copper, and I can just hit play on this specific print. Now, let me switch back over for the Q&A. All right. Okay, so I got a question here. What other materials does the Metal X print? So I showed a few of those before, but right now it's 17.4 pH stainless steel. We have A2, D2, and H13 tool steels. So depending on if it's a hot working or cold working application, you could choose one of those. We have now copper, Inconel 625, and then there's a few more on the way this year. One other stainless steel and titanium, and there might be one other one coming out. And in relation to that, there's also a question on how hard it is to change between materials on this system. So unlike a DMLS system where you have to vacuum out all the powder and you can't leave a single molecule of metal behind, on this system, all you have to do is run a purge line and have that new metal go through the print head. So it's about, I don't know, maybe a 5-minute operation or less if you have your Metal X already heated up. You would just hit unload material, pull out your old spool, load material, choose what material you're putting in. You run that material into the print head, and it'll just automatically purge out a little bit into. It's got a couple of brushes on the side that it'll purge out into. So very easy. How easy is it to post machine the different materials after printing? So all of these materials, and thanks Theo, all of these materials are going to machine exactly like the whatever that alloy is. So if you were to machine a 17.4 pH stainless steel, it would be as easy to machine as any other 17.4 pH stainless steel. So if there's specific metals, like some of these tool steels, the sintering furnace has an anneal option. So some of them are very hard and difficult to machine post-sintered. So you can also anneal it in the furnace, and that way you can machine it and then heat treat it afterwards. But as a whole, all of these are going to be machinable exactly as any other metal of that same alloy. Got a question from Tom. Can it be used to construct single traces on FR4 material to build small prototype PCBs? I will have to check on that specific. You're limited in how small you can print, so it'll depend on the specific part that you're trying to get. Send me an email with a specific question, or I'll follow up with you. I got your email here. So I'll get you a more in-depth answer on that. We have a couple of guys that are a bit better on the electrical side than I am over at Markforged, so I'll get more detail for you there. Awesome. All right, anything else? If anyone has, I forgot to mention this as well, if anyone has a specific part, oh, yeah, here we go. Yeah, if someone has a specific part like Dan's asking here, and you want to know where to send it, just send it to this email that's displayed on the screen, evan@neometricstech.com, as well as maybe a brief description of the application. We'll review it internally and give you a call, and we'll go over it on the phone. Any thoughts on aluminum in the future? So aluminum is very difficult to sinter, and that's the main issue with this system. We can 3D print it perfectly fine, but sintering it is near impossible right now. So Markforged doesn't have plans to release aluminum, as far as I know. That may change in the future if there's some sort of breakthrough on the R&D side. However, if there's a specific part that you have in mind for aluminum, let me know what the application is. There might be a workaround with a different metal. If you use aluminum because it's lightweight, if you use an infill pattern on maybe a stainless steel, for instance, you'll get very similar weight, but even higher strength. So on a part-to-part basis for now, we're going through, we don't have an exact one-to-one for aluminum yet, but there are metals that work for most of the applications. And if you haven't already checked any of this out, we also have composite materials, which are very close to aluminum strength. So you can 3D print a lot of your tools that you have on the production floor that you normally make out of a 6061 aluminum. You can 3D print them out of a composite material that also is printed on the Markforged platform, and that'll be very similar in strength to aluminum, but actually have better chemical resistivity and hold up just as well on the shop floor. So we'll have some webinars on that as well about composites and routing fiber, so be on the lookout for those in the future. Great. Okay. So if anyone has a question that comes to mind later on today, just feel free to email it over to me, and I'll get you an answer promptly. Thanks to everyone for joining this morning. Hope things are easy enough for everyone out there in this weird time. So, all right. Have a good rest of the day. Oh, sorry. One last question. Do we do parts as a service? Yes. If you have a one-off application or something that wouldn't justify buying a machine, especially a metal 3D printing system, email it to us and we'll get you a quote. All right. Thanks, everybody.